Hello. So, first of all, let me introduce myself. Mm, my name is Silvaraj Mabrook, and my student ID is BSCP CS 63122. So, this is the week 9 and the task 9.3 distinction. So, today I'm going to explain about the implementation of the Hack CPU using the computer.hdl code. So, let's look into the code first. So this was the proposed design as a question. So let's look into the code first of all. So the inputs are the in-im 16-bit. So uh, here is the in-im. So the M value input, it contains the RAM A, and then here the instruction C, the 16-bit instruction that's here. So it's gonna get to the execution. So here and then the reset. So this reset is the input. So this is the signal. So what happens is like if the program is executing, so without stopping, if it is executing, the reset will be zero. Or else like if it's restarting, since uh, for any issues if it resets, so the reset will be if it restarts, the reset will be 1. So these are the inputs, and then when we look into the output m 16-bit. So similar as the input, this is the output m value, and then write m. So what happens here is it writes to the m, and then here address is the same. It writes to the address m, so that's the data memory. And then the PC, which is 16-bit. So this is the program counter. So what happens is like it goes into it, like it gets into the next instruction. And then when we look at into the paths, so we'll look into the first section, and then we'll move on to below. So here what it says is not in instructions, this is 16-bit and the out is a instruction. So here the first bit of instruction is set to a, and if the instruction is 1, so is an a instruction. So here the input is the 16-bit instruction and the out is the a instruction since it's 1. Or else like here the input is the a instruction, so this is the invert, and then the output is c instruction. So what here it explains it says c as to 1, like previously the same as opposite, it says c as to 1 instruction. So if it is 0, it will get the output. So since it is 1, so the out is c instruction. And then when we get into the next one, here and bitwise operation. So in this part, uh, the inputs are the C instruction. Uh, instruction is the 6-bit, and then the output goes to the ALU to A. If the C instruction and D1 is set, then it will send the ALU to the A register. So that's what happening here. So and the next one is the Mark 16. So this what happens in this Mark 16 is the instruction and ALU out are the inputs, and it selects the ALU to A, and then the output gets to A region. So here also the A register receives the ROM's instruction. So that's what happening here in Mux 16. So when we get into O bitwise operation, so what happens here is the A instruction is the inputs A instruction and ALU to A, and then it loads the output to the load A. So this is the destination address. So what happens here is like if A instruction or ALU output is routed to A register, then what does is like it sets A register to write. So simply that's the thing. And then when we look into A register, the A array is the input and then it loads A and the output is A out. So that's the point. So when we look into mux 16, in this multiplex 16, the this selects between A register and M register inputs. So here it is A output and in M, so it selects as a 13-bit instruction, and then the output gets as M out. So this is what happens. But the thing is like it will select based on A or M, so based on the bit. So that's the thing. So when we get into next one, here in the AND bitwise operation, the C instruction and the instruction of the fifth bit is the input, and then it loads the output to the load D. So if C instruction and D2 is set, then the set D register is at right. And then when we look into the this part D register, so the input is the ALU out, which loads D, and then the output gets to D out. So we'll move on to this part, ALU part. So here the ALU receives A register and D register outputs. So this is what simply happens. Also, it's like the computer bits are allocated to dictate like what function to perform on which inputs. So simply that's the point here. So it's used to perform calculation, and then it sends the ZR here, the ZR and the NG bits um, to the ALU out. So that gets as the output since it is dictated below. So let's get into the memory part. So here what happens is like it provides the output for the memory writing. So in this 16-bit or bitwise operation, what happens is the A is the false and then B is the A out. So what happens is these inputs get into a selection of 15 bits, and then the output gets to address M. So this is what happens here. Simply like in simple terms, what happens is like it sends the A register value to memory to select the register and to read write. So that's what happens. When you get in this part, this O16, what happens is like this sends the ALU output to memory. Uh, so because the register is selected below, so that's what this sends the register to the memory. Sorry, the ALU to the memory. So uh, since the ALU the false is the input and ALU out is input, the output gets to out M. And in this part, this is an AND bitwise operation. So here what happens is the output writes bit to M register to the memory register, and the C instruction and D instruction is set. So on the fourth instruction and the C instruction, the write M gets as the output. So it's stored in write M. So when we look into the jump condition, so this is the jump condition. So here in this line, the AND bitwise operation explains that the ALU is equal to out. So uh, simply what happens is like this out is 0. So so once it's 0 and the JZ is set, then the JEQ will be the output. So the instruction within 2 bits and the Z route will get into the output as JEQ. And in this part, the input NG out and B instruction of 3 of the inputs are selected and got into the JLT output. So if ALU is negative, the J3 is set and then the JLT is used. So So this is the continuation of the second video. So let me continue from here, where the place where I stopped. So here, the AND bitwise operation, the NG out and the instruction of the third bit, the third instruction is resulted to the JLT as the output byte source in JLT. So it sends the if the ALU is negative and J3 is set, then the JLT is used as the output. So here in this part, in the OR bitwise operation, if ZR or NG is set, then uh, the output would be C equals 0. So either 0 or negative is the output. In this part, uh, in the NOT operation, the 0 or negative is the input and the opposite would be the positive. So the output would be the positive. So the ALU output is positive since the negative or 0 is input. So in this part, in the AND bitwise operation, so here if ALU output is positive and J3 is set, then JGT is also set as the output which is stored. So the positive and the instruction 1 with the input and it's stored in JGT. In this part, no bitwise operation. Here, if here J cube is set or here JLT is set, then the JLE would be the output. Because if ALE out is 0, if it's equal to 0 or negative, and then the program should jump is equal or less than 0. So that's why the output gets into JLE. In this part here, the OR bitwise operation, it jumps the condition not and then set the jump bit. So that's what uh, the data is stored in jump to A. The JLE and JGT are the inputs. So here in the AND bitwise operation, here the C instruction is the input and jump to A is input. So this selects and I guess the stores the values in PC load. So in this program counting load. So the C instruction and jump bit is used and then the uh, PC load results to the A register. So that's what happens here. In this part, not here it sets PC to default uh, to to the jump condition. So that's what happens is like the PC loads the input and the output is stored in PC in like the jump since the jump condition are not met. So it sets the default increment and in this part the PC the A output and the PC in is the inputs so which loads the PC load and then resets the program counter of 15 bits. So simply this is the explanation of the code. So uh, that's all. Thank you.